Swayam Prabha. Digital India. Educated India.
Today we will start on solving a few numerical problems, so that's why this tutorial 1 has been worked out, and this tutorial is based on some initial coverage, first maybe 6-7 lectures, where we will be discussing mostly on the crystal structure, the structure of the atomic diameters, vacancies, and things like that. So basically these are numerical calculations pertaining to the orderly arrangement of atoms. We had seen the source of strength to be orderly arrangement of atoms and management of defects, as well as the crystallographic planes, meaning crystal structure. So these are the three aspects which we will be covering quantitatively in this tutorial. So let's look at the first problem. We have the problem on iron, which has an atomic weight of 55.85 atomic mass units, and it has an atomic number of 26, which means that it has got 26 protons, and it has got an atomic radius of 0.126 nanometers. Estimate the density of iron at room temperature. Normally what we do is we calculate the density based on experiments, or we take an experimentally determined value depending on the alloy content of steel. For instance, we take the percentage of different alloying elements, multiply by the each by the density, and get a linear estimate of the density of that steel or alloy steel based on the alloying elements which have been added. So we see that atomic weight of iron is 55.85 atomic mass units. Atomic number is 26, that is, it has 26 protons, and its atomic radius is 0.126 nanometers. Estimate the density of iron at room temperature. Now, density of iron at room temperature depends upon the volume of the unit cell. So iron at room temperature has got a body centered cubic structure, and therefore number of atoms per cell is 2. There are 2 atoms per unit cell, right, for a BCC structure, and the corresponding value of lattice parameter A can be determined based on the expression A equal to 4R by root 3. So we know that the radius of the atom is 0.126 nanometers. So the corresponding value of A will be 4 into 0.126 nanometers upon root 3, and that turns out to be so many meters, 2.90993 into 10 to the power minus 10 meters. So we have found the value of A, that is the volume, that is the lattice parameter for a unit cell of iron, and then the volume therefore of one unit cell is A cube, right. The volume of one unit cell is A cube. Now if you take 55.85 grams of iron, it will contain Avogadro number of atoms. It will contain Avogadro number of atoms, right. Now one unit cell has got 2 atoms. So number of unit cells which are available in 55.85 grams of iron is 55.85 divided by 2, the Avogadro number of atoms, right. So I'll repeat that. The number of atoms that is available is Avogadro number of atoms divided by 2. right. So, it is half the Avogadro number of atoms. The number of cells which are available are half the Avogadro number of atoms. Okay. So, based on that, what we do is that we have atomic volume of molar volume has to be found out. So, volume per mole. So, volume per mole means that A cube, okay, into number of cells which are available, right. Number of cells available are half of Avogadro number. So, half of Avogadro number into A cube is the volume of the unit cell, that is volume of unit cells in 1 mole of iron, right. So, you have atomic weight is 55.85 grams divided by this volume of Avogadro number of cells, and that gives you the density as 7.526 gram per cc. Okay. So, this is how we calculate the density of iron. Normally, the density is something similar. So, this is a theoretically determined density based on the measured atomic radius and the measured atomic weight of iron. And so, based on the theory that the arrangement of atoms is in a lattice structure of body centered cubic at room temperature, we are able to estimate the density, and which is fairly close to the measured density. Second problem is about the comparison of vacancies per unit volume. Okay. We have 3 materials: cobalt, nickel and molybdenum. Okay. So, these cobalt, nickel and molybdenum have certain valencies, have certain number of vacancies, and so you have 8.9 gram per cc as the density for both cobalt and nickel, and molybdenum is 10.22 grams per cc, and the atomic weights are 58.93, nickel is 58.7 and molybdenum is 95.94. And we have been given that the Boltzmann constant per mole of atoms becomes a gas constant R, and so R is equal to 8.31 joules per mole degrees Kelvin. So, we have got a relationship between vacancy energy for vacancy formation with respect to the sublimation enthalpy, and we will use this data to arrive at the number of vacancies per unit volume based on the properties given here. So, as given in the previous slide, you have the density and atomic weight listed out here. So, number of sites per cubic meter, number of atomic sites per cubic meter are again 1.022 into 10 to the power 28 in case of cobalt. So, how do you calculate this? Again the same thing. You have again over 58.9332, atomic weight is 58.9332. So, you have Avogadro number of atoms, right, and in this similarly 58.7 grams you have Avogadro number of nickel atoms. So, this is the Avogadro number Na, okay, and the number of atomic sites per cubic meter as read off from that particular graph or as given from literature is 1.022 into 10 to the power 28, 6.416 into 10 to the power 28 in case of molybdenum. Now, the energy in terms of joules per mole is 185145 joules per mole. So, this is the activation energy that is needed for forming the vacancy. Okay, this is the activation energy that is needed for forming the vacancy. Alternately, you can express the energy for forming a vacancy in the form of electron volts per atom, and that is equal to 1.92 for cobalt, for nickel it is 1.73 and molybdenum it is 2.98. And so, if you have to convert this to per mole basis, then you need to multiply it by Avogadro number of atoms. So that will be electron volts per mole, and then you convert this into joule by using this factor 6.246 e to the 10 to the power 18 electron volts is 1 joule. So if you multiply this with Avogadro number and divide by this, then you will get the energy, activation energy in joules per mole. And so if you take the current vacancies at a given temperature, right, at the desired temperature. So what we are talking about is 1000 degrees centigrade as temperature. So now at room temperature there are certain number of atomic sites, that is potential sites for vacancies. Now based on the data which is given here, what we need to find is the NV at so N naught exponential minus q by RT will be the so N naught is this, okay. So these are the atomic number of atomic sites, exponential minus q by RT. So minus q by R is the gas constant and T is the temperature in Kelvin, and in our present case it is 1273 Kelvin, and so the number of vacancies per cubic meter turns out to be 2.56 into 10 to the power 20 in case of cobalt. In case of nickel it is raised to 22, and in molybdenum it is raised to just 17. Now this becomes a very crucial calculation, because the if you look at the three materials, cobalt, nickel and molybdenum, the presence of vacancies encourages diffusion, or presence of vacancies is one of the means of enhancing the rate of diffusion or diffusivity of alloying elements or atoms in the lattice. Now if the number of vacancies is smaller, then the corresponding diffusivity is also less, because the vacancies reduce the activation energy that is required for diffusion. So what happens is that in case of nickel, therefore the so called creep rate, I mean we have been talking about different properties. So creep rate is something that is much higher as compared to cobalt, and molybdenum is known for reducing creep rate, and the secret of that reduced creep rate, one of the secrets is a relatively low diffusivity. It is a relatively low diffusivity through the crystal lattice. Again it is no surprise, because molybdenum has a body centered cubic structure, whereas nickel has hexagonal close packed, where the diffusivity is nickel has got face centered cubic, where the diffusivity is the highest. So we know that FCC has got a very large volume inside the unit cell, due to which diffusivity through FCC is the highest, and HCP is in between body centered cubic and face centered cubic. So a hexagonal close pack still has got a higher diffusivity because of the empty space inside the lattice. So although these are close packed structures, nickel and cobalt, FCC and HCP, the diffusivity is much higher because of larger number of vacancies as compared to molybdenum. So this is 5 orders of magnitude compared to nickel, whereas it is 3 orders of magnitude difference between cobalt and molybdenum, and this makes a lot of difference when it comes to diffusion. And for things like creep, diffusion is a rate controlling process, and that is the reason why these vacancies matter a lot. Well, when you study creep, you might be able to you might want to recall this result. So that is the reason why we are just discussing it without really discussing creep as such. Now when we do alloying, the whole idea is to enhance the mechanical property, just as you saw the properties of cobalt, nickel, molybdenum, etc. So they have certain specialities, they have certain properties, they are able to withstand different conditions in service. And so, it is important that we do not rely on just one element or one metal. So, we alloy iron with say carbon, chromium for corrosion resistance, molybdenum for some creep resistance, silicon for again say strength basically. So, silicon adds strength to the material, manganese, vanadium. So, manganese partly added to fixed sulfur, very small amount of sulfur is present here. So, manganese reacts with sulfur to form small amount of manganese sulfide, because sulfur is quite low here, and you have vanadium, niobium etc. to control the grain size of the material. So, basically so this alloy P91 is an alloy which is used for making boilers, and it does not see such a high temperature. So, it is a water boiler. So, the temperatures do not go to those of gas turbines or some such equipment. They go to very high temperatures. Boilers go up to maybe few hundred degrees centigrade of temperature, and therefore, molybdenum is added to very relatively smaller quantities as compared to say superalloys or something like that. Chromium for corrosion resistance is important, because you have water which is heated to a high temperature, and the pH of water might not exactly be 7 at all times. So, because of that this chemical composition has been obtained for boiler grade steel. So, now the question is how much of carbon, chromium, silicon, manganese and molybdenum are present by percent volume. So, all this chemical composition has been given as per weight of the material. So, if I take 100 grams of P91 alloy, I have 0.1%, right. So, 0.1% is, so 1% is 1 gram, 0.1% is 0.1 grams. So, I take 0.1 grams of carbon, 9 grams of chromium, 0.92 grams of molybdenum, 0.23 grams of silicon and so on, and then I make that alloy of 100 grams. Now, the question is, it is by what I am doing is I have weighed everything and I have made that alloy as per weight. Now, the question is how many of these elements are present by percent volume. Okay. Then how much of carbon and chromium are present in atomic percentage per 100 atoms. Calculate the carbon equivalent for the above material. So, these are some of the things which you need to calculate from the data that is given over here. So, plenty of conclusions can be drawn from here. So, let us see the problem now. So, these are the elements for which these are atomic weight percentages which have been added, 0.1%, 9%. So, the same data which was defined in the problem has been copied here. Atomic weight of each of these elements is so for carbon it is 12, chromium 52, silicon is 28, manganese is 55, molybdenum is 96, iron is 56, vanadium is 51. So, the corresponding number of atoms, okay, so the corresponding number of atoms are so you have Avogadro number of atoms in 12 grams. So, in 0.1 gram you would have 5.019 into 10 to the power 19 number of atoms, right. So, you have corresponding value in chromium. So, you have for 52 grams you have Avogadro number of chromium atoms. So, in 9 grams you will have a proportional number of chromium atoms, right. So, that turns out to be 1.042 into the 10 to the power 21. Similarly, in silicon you have these many number of atoms present in the amount that has been added to the alloy, right. So, this way you have a certain number of, you have total number of atoms in 1 gram. So, number of atoms per gram is 1.085 into 10 to the power 22. So, this is the number of atoms in all. So if you add all the number of atoms present, you might get this kind of value. Okay. So the corresponding atomic percentage is at so 5.019 10 to the power 19 divided by this is 0.0046 roughly, and the corresponding percentage of chromium is 0.096. So you see that the atomic percentage is very closely related with the percentages which are mentioned here in weight as far as chromium is concerned. For silicon again it is 0.0045, for manganese again 0.0046%. So here it is, I mean everything added together, you get the atomic percentage, right. Okay. So now so if you take the overall percent, it is 1%. Okay. So now if you take the alloy of, let us say, instead of taking so many atoms, or instead of using this approach of calculating the number of atoms of each and then finding out the atomic percentages, right. If you find the number of atomic percentages, if you take this alloy to be a binary alloy of chromium and iron chromium alloy explains about 98% of the alloy content. So chromium and iron together constitute 98% of the alloy. So if you approximately take it to be that, neglecting other elements, so that iron and alloy of iron and chromium neglecting other elements, and using the formula which we have studied in during our discussion of binary alloys, how to find the chemical composition in terms of atomic weight percent, right. Not atomic weight percent, atomic percentage, right, atomic percentage. So here it gives, so how to convert weight into atomic percentage, that is the thing, how to convert weight percent into atomic percentage. So here you see that it is 9%, so 0.098, so 9.8%, and here it is 0.9019, that is 90.19%. So if you take these in terms of atomic percentages, the values are slightly different. So here you get 9.6 and here is 88.28%, this becomes 90%. Now there is hardly any difference between chromium percentage as calculated based on number of atoms compared to what is calculated when you consider it to be a binary alloy. That is because you have not changed anything with regard to chromium percentage. What you have changed is that you have assumed that the remaining 2%, we have said that 98% is chromium plus iron. So we have assumed implicitly here that that 9% is chromium and 91% is iron roughly. So instead of 98%, therefore we have assumed this to be 90%. So that is the reason why we are getting slightly more atomic percentage here. So what I am trying to illustrate here is that even if you take the main components, instead of taking all the minor contributions, if you take the main components constituting the alloy, still you can get reasonably correct estimates of the atomic percentages, right. Okay. So now if you take the density of each in gram per cc, because now we want to find out the content by volume. So first we have been given the composition in weight percent. Now we want to find out in terms of atomic percentages, that we have done, and now we go on to find out content by volume. So now you see that the density is in gram per cc is here, chromium 7.2, 2.33 and so on. So based on the based on the percentages of these elements, you get 7.8 gram per cc. Okay. Now let us see content by volume. So the content by volume is so much, because now you know that the weight percent and you divide it by the density. So you get content in terms of volume, and then percentage by volume, again you calculate the percentage. So total volume is 12.8 and so the corresponding volume percentage is 0.35 in this case, 9.69 in case of chromium, 0.76 in case of silicon, 0.49 in case of manganese. So now you are getting different atomic percentages, volume percentage, not atomic percentage, volume percentages. And so for molybdenum you are getting 0.69 as the volume percent. For iron it is 87.77, so it is close to 88% by volume. So this way you get different percentages by volume of these elements. Okay, yeah. And then we have been asked to find the carbon equivalent weight percent, and so what you get is C plus Mn by 6 plus chrome moly vanadium divided by 5, nickel plus copper divided by 15 plus silicon divided by 3. So then you get carbon equivalent as 2.27 in terms of weight percent, and I think as per volume percent you get is something like 3. So, so basically this is how you calculate the atomic percentages as well as the volume content of each of these elements in a given material. Okay. Now we come to the crystal structure. So we have FCC, BCC and HCP type of crystal structures, and here what we have we want to know is the distance of the nearest neighbors, meaning the lattice parameter A, and then interplanar spacing of 110 planes. Okay, so then you have for copper a face centered cubic structure which has got 4 atoms per unit cell, and atomic volume is given by 7.1 into 10 to the power 6 cubic meters per mole, which is equal to Na by 4 into A cube, because now 1 mole of copper has got Avogadro number of atoms, meaning material equivalent to the atomic weight of copper has got Avogadro number of atoms. Now number of unit cells is 1/4 of the Avogadro number of atoms, and the volume of 1 unit cell is A cube. So Na by 4 A cube is the total volume of the number of cells which are present in the in 1 mole of copper, right. So now based on this we have the therefore the molar volume given as 7.1 into 10 to the power minus 6 cubic meters, and based on this equation we get A, that is the lattice parameter, as 3.61 into 10 to the power minus 10 meters. So you multiply this by 4 and divide it by Na and then cube root of that. That is what has been shown here. So 3.61 into 10 to the power minus 10 meters. So this lattice parameter is known now. So now based on that you can get the value of dHKL. So HKL is 110. So you want to find out the interplanar spacing of 110 planes, and so this is 1, 1 and 0. So this is root 2, and that is the interplanar spacing. So this way you can find out the interplanar spacings of any HKL. So once the A is known, 1, 1, 1, 1, 2, 1, okay, 2, 3, 1. So it can be all kinds of planes for which you can find the interplanar spacing. Okay. So this problem is solved. Now we come to the Miller indices of different directions, as in case of crystals. We have seen crystal structure, but then crystallographic directions have to be defined. So what we do is that in a crystal structure you have this as the origin, you have x, y and z as directions. So when you take different directions, you have a head and a tail for every direction. So, this direction D has got a head. Now, in this figure, the tail, it is difficult to make out whether it is coming from here or from there. So, that is why we have taken two possibilities for D. For C, you have the head here and the tail over there. So, basically we need to therefore identify the coordinates for the head and the tail, and then subtract the coordinates of the tail from the coordinates of the head. So, you have these coordinates which have been identified based on these on this figure, and you get therefore the Miller indices as -1, 0, 1. So, this will be bar 1 essentially, bar 1, 0, 1. For B it is 1 bar 2, 2, C it is 4 bar 3 bar 4, D it is 0 2 1, and another possibility, if the D is from a different, so when the for D the origin is, so the tail can be either 0 0 0 from the origin or from 1 0 0. So, depending on that you get the Miller indices as bar 2 2 1 or 0 2 1, right. So, that is a slight difference it makes to the Miller indices if it were visually clear. Now, if you are given Miller indices, how do we sketch these directions? This is shown in this problem. So, within a cubic unit cell, sketch the following directions. You have bar 1 1 0, 1 bar 2 bar 1, 0 bar 1 2. So, what is the procedure? Now, you know that if you want to take bar 1 1 0, then you have this unit cell with an origin here. So, x is bar 1. So, you construct this line outwards, and then you have this positive y. So, bar 1 1 0. So, you have bar 1, that is x in this direction, 1 in the positive y direction, and z is 0. So, it is in the xy plane. The only thing is that it is in the negative direction like that. Okay. Well, you have the option of shifting the origin to this point. You have the option of shifting the origin to this point and then drawing this direction so that it lies within the cell. That is about it. But then you can always there is going to be only one origin for all directions. So, you draw this direction based on the origin which has already been taken as shown here. For B, bar 1 bar 2 1. So, for B you have bar 1 is -1, bar 2 is in the negative y direction. So, it is 2 units in the negative y direction and 1 unit in the z direction, right, and also 1 unit in the x in the negative x direction. So, negative x is here bar 1, bar 2, and then finally you go to 1. So, this is how you draw this, you identify the head of the. So, you notice that while in the previous case we had been given head and tail, and we were and the directions were all over the place, they did not necessarily start from the origin, right. So, for example, bar 1 0 1, while we inferred about the direction, you took this direction and inferred about it as bar 1 0 1. But if I am asked to sketch this direction, then what I will do is that I will take origin as 0 0 0, I will take bar 1 as so x in the negative direction, y 0, and z I will take as 1, and then I will construct the direction accordingly from the origin. So, what it means is that if I am to do that, then then what I have constructed, considering the starting point to be origin, will be parallel to this direction. That is the point. So, now if you take this bar 1 bar 2 1, you identify the position of the head, and the tail is by default taken as 0. So, that is why when you are asked to sketch the directions, the way to do it is this direction is understood to define the position of the head, while the tail is understood to be at the origin. So, that is the difference between the previous problem and this problem. Earlier problem you had the directions which did not necessarily start from the origin, but then you had to get the direction based on the head and tail coordinates. So, similarly it is 0 bar 1 2 is here. So, 0 bar 1 is again in the negative y direction, and 2 is in the, so 2 times in the 2 units in the z direction. So, that is how this direction is drawn. So, this way you can draw these, actually 6 directions have been shown. You can sketch the remaining 2 directions based on the practice that you get with these 6 directions. Okay. Now, in this problem again you have to identify the directions shown in the cubic unit cell. We have already done this problem earlier. Problem 5 was exactly the same. So, now I think you are equipped to take up this problem, and the answers are still given over here. So, what I would suggest is that you go through the initial few problems, and whenever a similar problem gets repeated, you do it yourself and then look at the answers. Do not look at the answers right from the beginning and try to somehow arrive at them. Try to solve each of these problems independently and then look up the answers. So, what I would suggest is take each of these problems, refer to the notes, refer to the lectures which have been done earlier, and based on those lectures try to work it out yourself and then compare the results. So, then I think you should be able to solve everything correctly, because things are fairly simple. Okay. In problem 8, indium has a tetragonal unit cell which has the A and C lattice parameters as 0.459 and 0.495 nanometers respectively. So, this means that the A, B and C, there are 3 lattice parameters. So, A and B are equal, and they are equal to 0.459 nanometers, and C is not equal to A and B, and therefore, it is 0.495, slightly more than the parameters A and B. Now, if the atomic packing factor and atomic radius are, so atomic packing factor is 0.693 and atomic radius is 0.1625 nanometers, we have to determine the number of atoms in each unit cell. Okay. Sketch the unit cell and sketch the directions 111, 333 and 110 in it. Use a separate sketch of the unit cell for each direction. So, that is what we are supposed to do. So, we have been given the A as 0.459 nanometers. So, we have got the volume of one unit cell as 0.104 whatever which is given here. Okay. So, C is this. So, based on this A and C, we have got the atomic volume. Now, we have got number of atoms which are present here as so this has got a tetragonal lattice, and therefore, we need to find out how many atoms are present per unit cell, right. Okay. So, it is this, now this has got the atomic packing factor of 0.693, atomic packing factor is 0.693. So, volume of one atom is so much, yeah, volume of one atom is so much, and therefore, now volume of atom per unit cell is given by that, and so total Vs is that, and the number of atoms therefore is 4 atoms. Okay. So, the volume of the atomic packing factor gives the volume of the spheres divided by volume of the unit cell, right, volume of spheres divided by volume of the unit cell. So, you have per unit cell 4 atoms are present, number of atoms present are 4 per unit cell, that is what it means. Now, when it comes to directions, the directions have to be sketched based on the learning in the previous problems. In case of directions, if the 3 Miller indices are multiplied by constant, so for example, here you have index of 1 1 1, it is multiplied by a constant 3, so that you get 3 3 3. Then the direction remains unchanged. Sorry, this spelling is wrong. Direction remains unchanged. In case of planes, one gets parallel planes. So if these Miller indices refer to planes, this will refer to parallel planes, but in case of direction, it is the direction remains the same, direction remains unchanged. So this is something which we should understand. Many times what happens is, if you are asked to draw these two directions, then people laboriously draw these 3 cells and then draw these this direction 3 3 3 and 1 1 1 also is in the same line. So therefore this additional effort of drawing 3 cells becomes unnecessary. So that is the reason why we actually it will be 9 cells. So this will come after drawing 9 cells laboriously. Here you can do the job in a single cell, right. So 1 1 1 and 3 3 3 directions are the same. So if you are asked to sketch, you just sketch 1 1 1 and label it as 3 3 3 as well, because it will lie in the same orientation. However, 1 1 0 is different direction. So you have 1 1 and 0. So in the previous exercise we had done a bar 1 1 0. So instead of this going to the negative side, x is in the positive side. So it is 1 1 and 0. So your vector will be something like this. So that is it. So number of Miller indices for the planes is given in this figure. So you have we need to determine the Miller indices. So now in planes the procedure is slightly different. You take the intercept with respect to x, y and z plane. So it is 1/3 for x, half for y and half for, actually it is minus half for z, right, because now we have the origin which is somewhere here, right. So origin is somewhere here, so half and this is minus half. So as a result, if you take the reciprocal, we will get 3 2 and minus bar 2. So that is the Miller index for this plane A. Now for plane B, we shift the origin to the to here, because here x is given as, x is minus half actually. So here it is 0, z is plus half and y is infinity, because it doesn't it is parallel to y. So the intercept is minus half, infinity and half. So minus half, infinity makes it, here it is 0 and this is plus half. So although it is so you have it as bar 1 0 1, right. So if you multiply everything by 2 and then you will get bar 1 0 1. So essentially this plane is not bar 1 0 1, it is actually plane which is parallel to bar 1 0 1, but then it has got the same kind of indices. So what this means is that if you again, as we saw in the previous example, if you multiply it by a constant, then it forms a parallel plane. Now you have this plane. So where will this bar 1 0 1 lie? So we have shifted this origin here. So bar 1 will be here. Then so it will be, one edge will be this way, right, and then 1 is z is equal to 1, and therefore one edge will be this, other edge will be that, third edge will be here, and the fourth edge will be coincident with this dotted y axis. So this will be bar 1 0 will exactly be parallel to plane B. But instead of saying it is minus half 0 1, okay, 0 1 half, we say that it is bar 1 0 1. So, the indices are given in an integer form. So, it is very important that the Miller indices are given in an integer form. In this problem, well, now we have to sketch these planes in a unit cell. So, the procedure is the reverse. So, based on the unit cell, based on the Miller indices, you calculate the intercepts and then mark the intercepts accordingly. So, it is 0 bar 1 bar 1. So, now since it is y and z are both negative, you would shift the origin to the right hand corner. You would shift the origin to the right hand corner over here, so that this is the negative y direction. So, this point becomes bar 1 for y, and this point becomes bar 1 for z. So, this is z equal to -1 here. So, now what we do is that since the plane is parallel to x, okay, so the plane is parallel to x. So, we take this direction, this is x, and then you have bar 1 which goes up to here. So, the intercept with y is negative, because now you have taken the origin somewhere there, and the z intercept is also in the negative direction, and therefore, so you have this plane this way. So, actually the way the plane has been drawn is wrong, because here you would have this edge, an edge going this way, you will have x. So, since it is parallel to x, you will have this edge, and then the fourth edge will be this diagonal to this this plane over here. So, you will have therefore 4 edges, 1, 2, 3 and 4 as the edges of this plane. If you take 1 1 2 bar, okay, 1 1 2 bar is drawn over here. Now, here what they have done is that the planes have been drawn without shifting the origin. So, actually in real practice you should shift the origin. So, you need to so the reciprocals will be 1 1 and -12. So, if you shift this origin to this point, that is z equal to 1, then you will get -12 over here, right, and then you have 1 1. So, 1 1 and -12 will be the plane which will be somewhere here. So, although these planes would be having from the similar family or something like that, but still it is important to shift the origin. So, it is very important to learn to shift the origin and draw these planes. So, in all these figures, the one issue is that the origin has not been shifted, although it should be shifted. In fact, in the previous examples we did see the shifting of the origin, right. So, the same thing is required over here. So, no plane should go outside the crystal lattice, that is the idea. So, here like for example, this plane is going outside the crystal lattice by a little margin. So, had it been shifted, had the origin been shifted to here. So, this is 1 bar 3 1, this plane D 1 bar 3 1. So, 1/3 is the intercept, -1/3 is the intercept here. So, you would have got 1 bar 3 and 1. So, as another triangular plane over here. So, basically what it means is the plane has to be drawn by shifting the origin. So, the error here is that origin has not been shifted. The procedure remains the same. So, first step is convert the Miller indices into reciprocals. The reciprocals will tell you the intercepts and mark off the intercepts. If there is a negative intercept, shift the origin in that particular direction. For instance, you have intercept of -1 and -1. So, you shift the origin to 1 unit in y and 1 unit in z direction. So, you shift the origin over here. Bar 1 1 bar 1, so you shift the origin here and there. So, you shift the origin to somewhere here, so that you get 1. So, when x is bar 1, you get that point over here, and 1 when it is 1, you get that point here, and z of bar 1, you get this as here. So, basically you get these 3 points. So, the 3 points which are 1. So, z is bar 1. So, z is bar 1 here, x and z are bar 1 and y is 1. So, you get the plane as 1, 2 and 3, right. Yeah. Okay. So, you get the plane z is bar 1 here, x is bar 1, so x bar 1, z bar 1, and so y is 1, right. So, we join these 3 points and we get the plane 1, 2 and 3. So, we get a triangular plane. So, basically the plane comes inwards, right. So, instead of going here, you get this plane inside the lattice. So, you get yeah. Now, we come to the Miller indices for hexagonal close packed structures. The Miller indices are in 4 are not represented as 3, but they are represented as 4 coordinates. So, one is A1, A2 and A3. The 3 axes are there, each at 120 degrees. But then the procedure for determining the Miller indices is the same. For instance, you have Miller indices for planes in HCP structure, where you have for this plane, now this intercept is 1 for A1. For A2, it is parallel to A2. So, intercept with A2 is infinity. With A3, okay, it is -1. So, A3 intercept is -1 here. So, A1 intercept is +1, A3 intercept is -1, A2 intercept is infinity because it is parallel to A2, and Z intercept is equal to 1. So, you take the reciprocals and then you get 1, 0, bar 1, 1. So, 1, 0, bar 1, 1 is this plane. Similarly, the basal plane, which is this hexagonal plane, has got Miller indices of 0001. That is because it forms it is parallel to all the planes A1, A2 and A3, and then it forms so only with z equal to 1. So, you have this z equal to 1. So, you shift the origin to the top. Now, the rule of shifting the origin applies to planes which pass through the origin. So, that is very important. So, that you shift the origin there and you get, otherwise you will get for this basal plane, for example, 0, 0, 0 as the no, that is not acceptable. So, you take at the top one the top plane as the origin. So, that now you shift to the by 1 unit to the to a parallel plane here. So, you get 0001. So, you have the intercepts as infinity, infinity, infinity and 1. So, this way you have 0001 as the coordinates. Similarly, this plane, this is a kind of prismatic plane. So, you have now this plane has an intercept of 1 with A3. It is parallel to A2 again, and it is parallel to z as well. So, that is why it has got intercepts of infinity with respect to z, and then with A3 it is 1, and with A1 it is exactly equal to -1, right, the intercept is -1. So, A1, A2, A3, A4, A1, A2, A3 and Z. So, you have bar 1, 0, 1, 0 as the reciprocals, which signify the Miller indices for this plane. Now, one thing to be checked is that the third index should be minus of the sum of the first two indices. The third index should be the negative of the sum of the first two indices. So, that is what we see here also. So, this is 1 plus 0 and the third index is -1, right. So, that check has to be made, so that you can also be sure that your indices are correctly determined. Other planes, let us say you have A1, so you have A1 axis here, so intercept is 1, A3 is -1 as shown over here, and then it is parallel to A2, so intercept is infinity and C is equal to 1. So, then you have the Miller indices 1, 0, bar 1, 1. Here A1 in this plane, A1 is equal to 1. So, earlier we had seen a vertical plane that was a part of the hexagon. Now, this is not a part of the hexagon. So, this plane makes an intercept of -1 with respect to A3, okay. With C it makes an intercept of infinity being equal to being parallel to the z axis. With A2 it makes an intercept of half, okay. It makes an intercept of half, and A1 it makes an intercept of -1. So, this is positive A1, here in the center is origin. So, here you have negative A1. So, you have -1 as the A1 intercept, half as A2 intercept, -1 as A3 intercept. So, because this is minus A3 direction, the positive A3 direction is in that direction, right. Yeah. So, it is A3 is -1 and C is infinity. So, the corresponding reciprocals are -1, 2, bar 1 and 0. This plane now has got reciprocals, so not reciprocals, the intercepts as A1 is equal to half, right. A2 is -1, so A2 is -1, positive A2 is in this direction, whereas the intercept is there. So, A2, A3 is again -1 because it is in the negative direction of A3. So, minus A3, and C is equal to 1. So, it has got an intercept exactly of Z equal to 1, and so when you take the reciprocals it is 2, bar 1, bar 1, 1. Now, you have to check whether the third index is negative of these two, the sum of these two indices. So, 2 minus 1 negative of that, right. 2 minus 1 is 1, negative of that is -1. So, the third index is the same as -1, and therefore, our answer is correct. Okay, so, this is the solution to problem number 12. Now, we come to the solution of problem number 13, where you have different planes and you now have to find the planar densities for this plane. So, what it means is that you need to find out the number of atoms, the number of atoms per unit area of the plane. Basically, that is what it means, right. And so, we have different areas. So, here if you see, here you have 1 quarter of each atom, 4 quarters of atoms. So, you have 1/4, 1/4, 1/4, 1/4. So, 1 atom per plane divided by the area. Area of the plane is A square. So, 1 divided by A square is the area of this plane. Now, here what you see is that here it is quarter, 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 quarter. So, 4 quarters makes it 1 atom. The central atom is full atom. So, you have 2 atoms on this plane, and this so this is a 110 plane. What we saw earlier was a 100 plane. So, in this 110 plane, in this 110 plane, you have the number of atoms as 2 and the area of the plane is a into root 2 of a. So, because this length is root 2 times a. So, root 2 a square is the area of this plane, and there are 2 atoms, so 2 divided by root 2 a square is the planar density for this plane. So, this shows which plane is more close packed, right. So, here we had 2 upon root 2 a square. So, you had basically root 2 upon a square. Here you had the planar density of 1 upon a square, and now here what you see is that there are again 3 atoms, but they are not quarter. Now, each triangle is an equilateral triangle, right. It is an equilateral triangle, and each side is root 2 a square, right. Root 2 a square is this side, this is root 2 a, root 2 a is this length, root 2 a is this length, because this is a square. So, this is a, so 2 a square, so this is under root of 2 a square. So, it is a root 2, right. So, this is a root 2, a root 2, a root 2. So, equilateral triangle. This angle subtended is 60 degrees, this angle subtended is 60 degrees. So, this encompasses 1/6 of this atom, corner atom. So, the corner atom is 1/6 here, 1/6 and 1/6. So, 3 into 1/6 makes it half. So, 0.5 atoms here, and then the area of this plane is 1/2 of base into height. Base is root 2 into a. So, 1/2 of root 2 a into the height, which can also be calculated using the Pythagoras theorem. So, basically it is important to get the area of this plane and get the planar density. And then the question is, which crystal structure do the figures represent? It is the body centered cubic structure. That is because this body centered atom is completely on the 110 plane, and then there are no extra atoms on the 111 plane. For example, you have in a face centered cubic, you would have had an extra atom here, here, similarly here. So, you would have had 3 more atoms, and they would have been 50%, right. So, the atomic packing density in the FCC structure for the same plane would have been much greater than what it is here for a body centered cubic structure. So, based on these this sketch, it shows that the crystal structure is a body centered cubic structure. Okay. So, with this we complete the tutorial problems. Try to solve them yourself, and then refer to the material which has been already given to you, and I am sure you will be able to solve them yourself. Thank you.